Our agenda today is non-thin wall shearing stress. Just a reminder, term test 2, July 4th, 6:30 p.m. to 9 p.m. in person. It is in the same room. I'll put on Avenue to learn what room it is. You're going to have 3 questions like before. Questions will be similar to homework 3, homework 4, and examples from week 4, 5, 6, and 7. So, i.e., today's topic will not be tested in the second term test because you only have 1 week to learn, and it's not fair to test you on something that you just have 1 week to learn. Okay, so I repeat again, today's lecture will not be tested in term test 2. Right, so today we're going to go into non-thin wall shearing stress. Okay, so if we have a cantilever beam, okay, so if we have a cantilever beam, okay, so this is our cantilever beam. Right, and we have one at point A, and the other part is point B. Okay, and then we have a load acting down over here, which is equal to P. Okay, so if we were and I will address our transformation, this is our point X, x-axis, Y, and then we have our rotation about Z. Okay, so when we have a structure like this, I'm going to sketch our free body diagram now. Okay, so our free body diagram will look like this. Okay, so we have our beam, right? And we use static analysis. Okay, so we know that if P is coming down this way, we will have a force going upwards. And this is your AY. And then we are going to have a counter moment over here. So this is our moment at point A. Okay, our moment at point A. So if you look at this structure, which is a cantilever beam, okay, and I'm going to specify we have a length over here. And our length is L. And we know that over here, failure will occur at point A. Okay. And why failure will occur at point A? If we were to now sketch our shear force diagram, okay, if we were to sketch our shear force diagram, okay, so this can be in V, which is our shear force, and it also can be M, which is our bending moment. Okay, and we know how the shear force will look like if this is P, all right? So this is our 0, and at a certain point, this is our point L, length L, and we have our shear force doing this, okay? And then it'll come down vertically. That is our shear force. And then for our bending moment, right? So this is our shear force. And our bending moment, okay, will go like this. Let me give it different color. Okay. So over here, our mx is equal to P multiplied by L. Okay, that's our mx. So the failure at x is equal, so this is our x is equal to 0. This is also our point A. The failure occurs due to twofold. Okay, the failure occurs because we have maximum bending moment, and we also have a shear force that is also at its maximum, that's P. Okay, so now if we were now to look at, if we were to look at this in 3D, okay, so we go look at this in 3D. So this is X, this is Y, and this is our Z. So now if we were to sketch this diagram in 3D now, okay, so I'm going to sketch this diagram in 3D. Okay, and again, this is our point A. This is our point B, right? And then like what we had before, we have a load coming down over here. There's P. Okay, and I'm going to, so the failure will occur at point A, as we mentioned. Now, if we were to place an element, okay, so you guys know what is an element now, right? We just finished mole circle, right? So if we were to place an element down here, right? If we were to place an element down here, and if I'm going to expand, so this is our element. Okay, this is our element, or okay, not exactly over, or we just place it. I do apologize for this. If we were to place our element over here, okay, our element over here. So I'm going to expand the view of the element, right? I'm going to expand the view of the element. So now the element looks like this. Okay, the elements look like this. So the element is going to carry two different stresses. And the first one, okay, we know that it's going to carry a normal stress. It can be tensile or compression, depending on where you look at. So this is our stress X, right? And this stress X is because of what? It's because of mz over izz multiplied by y, okay? Then we're going to consider the shearing stress, okay? The shearing stress, because P is coming down in a vertical direction, the shearing stress now will look like this. And you guys know that this is known as negative shear. Okay, wrong color. I should use a different. Okay, so we have a shear like this. And the shear, what we call this shear, is shear. The intersecting plane is X and it's coming down in Y direction. Now, over here, the shear will be equal to Vy, okay, because the shear force is in the Y direction, over Izz, right, multiplied by Qz divided by T, okay, where Vy is the shear force, and it can be in Newton or it can be pound, And then we have our IZZ, which is our second moment of area about the ZZ axis. Units can be in meter 4 or inches to the power 4. QZ represents our first moment of area. It represents our first moment of area, and the units is in meter cube or inches cube, and QZ is equal to A y bar, okay, where A is the cross-sectional area, okay, and y bar is the centroid of the area. And finally, T represent the thickness of the structure. Okay, so let me put in some units. This can be inches squared, a meter squared of inches squared. The Y, it can be meters or inches, and the thickness can be in meters or inches. Okay, so you can see what we are trying to determine now down here. Okay, we are trying to determine both the normal stress, okay, and also the shear stress acting on the element. And once again, okay, the failure surface is over here. So what I'm going to do now down here, this over here is the failure surface or the failure plane. Okay, so if I'm going to draw this shaded, right, this surface where fracture occur, that is going to be the same thing over here. That is going to be a failure plane. So we do know how the normal stress is acting on that face or at that plane. Okay, so the plane that we are talking now down here, so this plane that we are focusing down here, this is our YZ plane. Okay, where fracture will occur. Okay, so for this chapter, okay, we are going to focus on how to calculate the shear stress. Okay, how we can determine the shear stress. Okay, so now, the next thing that I'd like to introduce to you, so now you know that we are going to calculate shear. The next thing we are going to I'm going to introduce to you is known as the shear flow. Okay, and the formula very similar to shear stress is Q is equal to V over I multiplied by Q. The only thing we omit is what? Is the thickness, right? It is, if you were to compare over here, okay, the shear stress. So over here, you have V over I multiplied by Q over T, right? For the shear flow, is Q is small q is equal to V capital Q divided by T. And Q represents our shear flow. Okay, represents our shear flow. And the units, okay, so the units is in Newton per meter. Why that's the case? Because if we look at units over here, right, the shear force is Newton. The first moment of area is meter cube. The second moment of area is meter 4. You get rid of this, you have Newton per meter. Now, you ask me, Eugene, what is the shear flow physically? Okay, what is the shear flow physically? So now if we were to look at the cross-sectional view, so now I'm going